So let's look at a problem like the following. Let's say a quadratic function is given to us in the following way, with minus here, and let's say minus 8. Is this a quadratic function? Yes. And what is special about it? It has the square, what? It has the square completed. It has the completed square in it. Good. So this should not give us any difficulties because in chapter 2, we talked about transformations. So how do I graph, or what is the base function used here?
X squared.
Right. So this is my x squared, correct?
Mm-hmm.
Good. What is the first transformation? Remember, everything has to be in order of operations.
Left 4.
Left 4. Okay, I'm going left 4. Now, the negative 2 in front is 2 transformations. And now we have to,
What's about the...
first let's stretch.
Right, okay.
By a factor of 2, then what do I do? Reflect.
Left,
Good.
Y,
And then?
vertical.
And then what do I do?
Down 8.
Down 8. Can anyone give us the vertex? One more time. Let's start from scratch. X squared. X plus 4. 2 times x plus 4 squared, of course. Negative 2 times x plus 4 squared.
-4, -8.
Do you all agree with negative 4, negative 8? Can you already give me the range? We haven't even graphed the function. We just thought of transformations. Can anyone give us the range?
But I should. It's negative infinity to negative 8.
That's it. This is what we already know about the function. Why? Because it had that square completed. We could have not done that for the other function that did not have the completed square. Very good. So now we already have the picture, but let's start slowly. What is the shape? What is the shape of this function? And how do I know?
Parabola.
Well, yes, but the question for the shape is if it opens upward or it opens downward, and how do I know? I already know the answer because I use transformations, but how do I know if I don't use transformations? How do I know whether it opens upward and has a minimum or it opens downward and has a maximum? The what will tell us?
Leading coefficient.
Very good. Since the leading coefficient, this is the leading coefficient. A equals negative 2, which is a number less than 0. The parabola will have a maximum or a minimum. One more time. Maximum. This is from last time. So when the leading coefficient is negative, the parabola has a maximum. And let me put in parentheses, when the leading coefficient is positive, the parabola has a minimum. This is not our case, but I just put it in parentheses as a reminder. Good. Step number 2, the vertex. In this case, I don't have to calculate it because I already know it. What is the vertex one more time? Not Tom. You're not punished.
I know.
Can anyone give us the vertex?
-4, -8.
Thank you very much, Eddie. Good. Step number 3, X-Intercepts. And remember, they come with if they exist. We already have the picture. We already have the graph in our heads. One more time. X squared, x plus 4, 2 times x plus 4 squared, negative 2 times x plus 4 squared, and negative 2 times x plus 4 squared minus 8. So, will this function have? Should I look for x-intercepts? No, none. Very good. Number 4, y-intercept. How do I get the y-intercept for any function? I said, very good. So I have to find f of 0. Let's do this together. 0 plus 4.
4.
4 squared.
16.
16 times negative 2. He can't even talk in his sleep.
32 on that. It's like
Negative
somewhere right
32.
down.
Negative 32, and then minus 8, negative 40. So can anyone give us the ordered pair that represents the y-intercept? Very good. 5, 6, and 7. 7 is the range. You already gave me the range. Can you please give it to me again?
Negative 30.
Very good. Awesome. 5 is the axis of symmetry. And one more time, does this function have a max or a min? Max. So I'll say max value of this function is, max value of this function is, where do I read it from? Where do I read the maximum value for this function?
From the range.
From the range is 1, or from the
Vertex.
from the vertex. So what is the maximum value? Negative 8. And what is the axis of symmetry? Remember, the axis of symmetry is the vertical line passing through the vertex. What is the vertical line passing through this vertex?
Negative 4.
Yes, but I have to write it as an equation.
X equals negative 4.
Very good. Ready to graph? Because I already pictured the graph in my head, I know that I don't really need the positive side of the y-axis that much. I look at the y-intercept and I see it's negative 40. So I'm going to say, I'm going to take a certain unit that will allow me to get to negative 40. So let's say 10, 20, 30, 40. I don't start with the y-intercept. I did in this case because it's such a big negative number. Okay, I have to start with the vertex. So 1, 2, 3, 4, and this is negative 10, negative 40. So my negative 8 will be here. There are no x-intercepts. My next step has to be the axis of symmetry because I'm trying to keep the graph in shape. And as you know, this is not part of the graph. So this is x equals negative 4. And now I'm ready to graph and try to make it as symmetric as possible, not too acute at the vertex. So this is the graph of f of x, negative 2, x plus 4 squared minus 8. With a graphing calculator, please plug it in y equals, clear if you have anything else. Negative 2 in parentheses x plus 4 squared, and then minus 8. Since I already have the graph, right, I know that the maximum is at negative 8, I will have to adjust the viewing window. I don't care for the positive side of the y-axis, and I don't care too much of the positive side of the x-axis either. So x minimum, I'm going to say negative 8. X maximum, I'm not going to go beyond 4. That's good enough. Y minimum, negative 10. Well, no. I need to see at least negative 40 or below. So I'm going to put negative 60. And for y maximum, the positive side, I'm not going to waste too much time on that. So it's just 2. And I am going to put this scale at 10. And then graph. So I had to make those adjustments in order to see this graph. Okay, here it is. And here's the maximum at negative 4, negative 8. It does not, the graphing calculator does not graph the axis of symmetry, but we do have to graph it. So here is the y-intercept at 0, negative 40. Any questions? Any questions? Okay. If you don't have anything else for me, I am going to consider 3.2 done, which means all these problems should be done as soon as possible so you can ask questions and be prepared. Okay? So I'm kindly asking you to solve the, yes, please, Brian?
You said that the date that we had to review that test.
I extended for 2 weeks.
Okay.
Yes, 2 weeks from today. But let me know as soon as possible if there is any glitch.
Okay.
Don't wait till the last moment.
Right.
Okay? So I'm given 10 points for a very good grade, let's say at least 90%. And I'm giving another 5 points later on to redo it. Okay? And before the final exam, I'll give another incentive for you to redo that. So to cement the information and be ready for the final. Okay. Other questions for me? Oh, I didn't mean 3.2. I'm sorry. I'm doing 3.2 right now. So at the end of the day today. Okay? So 3.2. So one more time, I would like you to bear with me in 3.2. The first problem, you may take like 15 minutes, but the subsequent problems will take 2 minutes. But the first problem will take some time because I have a lot to tell you. And I just wanted to show you in your book, if you pay attention, you will not have to, which I'm not saying you shouldn't, you will not have to read these 15 pages. 1, 2, 13, 14, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13, 14. You will not need to do this. So please pay attention. I'll do as many problems as we need to go over. Okay. So this is section 3.2, which deals with polynomial functions. And again, you may say, but what was this that you just taught us in 3.1? Yes, it is a special type of polynomial function. They're all special in a way. It was quadratic. So this, when we talk about polynomial, we really mean degree 3, 4, 5, 6, and so on and so forth. That's what we mean when we talk about polynomial. Otherwise, we will say linear, quadratic. Do these have names? Only this one, cubic. But the rest, not really.
You could, but we don't really use them.
Correct. So we really don't need, Tom is right. We really don't need to specify. We just say.
Quintic, but nobody ever really
Correct.
uses it.
I agree. So then we'll say just degree 4, degree 5, degree 6. Okay. Here's the list of items. As we had here, a list of 7 items. We have some of these will be in the list for polynomials, and others will be added today. Okay? So this is the list of things that we have to show with the quadratic. So now I'm going to list the items for polynomial functions, degree 3, 4, 5, 6, and so on and so forth. Step number 1, domain. And you could say, wait a minute, you didn't have domain here. True, because this was a function that we knew very well. Okay, and we do know polynomial functions have specific domain, which is what? Always at
All real numbers.
All real numbers. So then why mention it? If they all have all real numbers, why wouldn't I would even mention it? For the next section in which we deal with rational functions, I would like us to get used to determining or putting the domain in there. Okay, number 2. X-intercepts. And now I'm going to add something that we haven't discussed before, ever. And their multiplicities. Multiplicity, plural multiplicities. So we will be determining the x-intercepts and their multiplicities. Step number 3. Not necessarily in this order, but domain should be the first, always. Step number 3, y-intercept. Step number 4, degree. Very important to identify. Step number 5. Max possible number of turns. We haven't had this before. No, maximum possible number of turns. In other words, by a turn, we mean max or min. We can never ever talk about vertex again. The vertex is specific to the quadratic function and only to the quadratic function. We cannot say that we are looking for vertices. That's not possible. The word vertex refers to quadratic functions only. So we have to say turns or max min, but not vertices. Okay. Step number 6. Something again that we haven't talked about. End behavior. Step number 7. Symmetry. Step number 8. The values of max min with TI 84. If you have something else, it's fine too. But I have 84. So quickly, domain. X-intercepts and their multiplicities. Y-intercept, degree of the polynomial. Maximum possible number of turns. End behavior. We haven't talked about that. And we haven't talked about maximum possible number of turns either. Symmetry and the values of the max min with the graphing calculator. Okay. So if you have your book, I will invite you to pick a problem that is degree 3. If you don't have a book, then you'll trust me that I will pick one that has degree 3. As I said, the first problem will take a long time because I have a lot to tell you about all this list. So would you like to pick a cubic function or a third degree, or would you like me to pick one? Say it again, Ryan?
So I think the better question is, does anybody have a book?
That's fine, I do. I will pick a problem. Okay, I would like to pick, yes, 50. I don't like doing odd number problems, but this is a problem that it's specific for what I need right now. So I'm going to pick 53. And this is on page 378. And it's 3x squared minus x cubed. Okay. The question is asking us to graph it. And no, we are not going to grab the graphing calculator, punch it in, and copy the graph. No, that's not what we are going to do. Okay. Before we even start the problem, let's go through this list and see what we know and what we don't. I already said it, but let's just go over. Okay. Domain. Do I know the domain of this function? Which is? Correct. Do I know the degree of this function?
Yep.
Good. So I'm going to start a table. You already gave me the domain. So I'm going to write negative infinity to positive infinity. Next to my table, I will write degree. Can anyone give us a degree? Very good. So from this list of 8 items, I already have the answer to 2. Now I would like to continue with the x-intercepts. First, I'm going to ask myself, how many x-intercepts, and I would like you to answer, how many x-intercepts will I be looking for? Not Tom. He's asleep, so let's talk quietly.
The fact that I'm talking should be evidence.
So how many x-intercepts will I be looking for? How many? Okay, what do I have to write? So in order to find the x-intercepts, what do I have to write? I equal to 0, I didn't hear the first. Yes, the function, very good. Or y, perfect. So then I have 3x squared minus x cubed equals 0. One more time, how many x-intercepts will I be looking for?
1 or 3.
Exactly 3. If the degree is 3, I have to look for 3 solutions, no matter what. They may be all the same, I don't care. If the degree is 3, I have to look for 3 solutions. Perfect. Good. So what will you do first in order to solve this equation? Okay, what do you think I will do first? Not there yet? Now you already know me. I'm looking at 2 keywords, action words, all the time in math. What are they? What are the key action words? Factor and
symmetry. Simplify.
Correct. That's, if you give me anything, my first 2 thoughts are factor, simplify. And this is not ready yet. It's not cleaned up. How do I clean this up?
Well, it's not in order.
Awesome. That's my first thing, yes. Very good. That's the first key. The first key word, if you want. Descending order. Awesome. Then what? What should I do next? Not yet. It's not cleaned up yet. What is the problem now? On this one, the problem was it was in descending order. Now I have another problem here. After I presented it in descending order. Correct. Absolutely. I refuse to solve any equation with a negative leading coefficient. I refuse. You will never be able to force me to do that. So multiplying both sides, I have this. Now it's completely cleaned up and waiting. So what should I do? What is my next step towards solving this equation for x? What will be your next step? You will, yes, now I'm ready because it's cleaned up. You said, yes, what will I factor out? Very good, awesome. What is left in parentheses? Perfect. Now I need 3 solutions. Can anyone give us 3 solutions for this equation?
I can tell you one where it can't be.
This is not a rational. This is not a rational. We don't set it not equal to.
Okay.
We're trying to find the x-intercepts, and this is a polynomial. It's defined everywhere. We cannot exclude anything from the domain. Can anyone give us 3 solutions? Can anyone give us 1 solution?
3.
Yes? Yes? How many times? Twice. Because x squared means x times x. So there are 2 solutions, x equals 0. And 1 solution, x equals 3. Very good. This is what we call multiplicity. How many times does x equals 3 appear as a solution? So we say multiplicity 1. How many times does x equals 0 appear as a solution in, or as a 0, or as an x-intercept? How many? Right. So I'm going to say multiplicity 2. So x equals 0 has multiplicity 2, x equals 3 has multiplicity 1. What is it so special about it? So let me explain the multiplicities, and I'm coming back to the problem. Multiplicity. They are of two types. Odd multiplicity has nothing to do with symmetry. In other words, this is x equals 3 has a multiplicity, an odd multiplicity, because it's 1. X equals 0 has an even multiplicity because x equals 0 appears twice. So a multiplicity can be an odd number or an even number. So here's what happens when an x-intercept appears an odd number of times. Like it appears once, it appears 3 times, 5 times. If it appears once, so multiplicity equals 1, it's just a regular cross like a linear function. Now, if it appears 3 times, do we remember the graph of x cubed?
It's like a
Right.
backwards F.
For x cubed, if you set x cubed equal to 0, how many solutions does that have? X cubed equals 0. How many solutions are we looking for?
3,
Of course, and they are all
0.
exactly. So it's a 3 solution x equals 0, multiplicity 3. When I graph that function, do I graph it like this, or do I graph it like this? Because there are 3 solutions in there. So multiplicity 3 looks like this. It's a cross. They're all crosses, but a flat or slow cross. How will a multiplicity 5 look like? Still a cross, but even slower than this. Still one intercept. One touch with the x-axis, but much slower than this. Something like this. Finally crossing. See the difference between these 3? This is taking more time than this. This is fast. Multiplicity 1. Multiplicity 3 takes its time. Multiplicity 5, it's even slower. Okay.
5.
Let's talk about even multiplicity. Do we know a function that has 2 solutions in one spot? Exactly. So every time the multiplicity is an even number, that would be a turn, not a cross. It will not cross the x-axis, but it will turn. This is multiplicity what? Anyone? Very good. What is this? Definitely not 2. But still an even multiplicity. And so on and so forth. So what have we learned? If a 0 or an x-intercept appears once, 3 times, 5 times, or an odd number of times, the function at that x-intercept will cross the x-axis. Multiplicity 1, fast cross. Multiplicity 3, slow cross. Multiplicity 5, very slow cross. If a solution appears, an x-intercept appears an even number of times, that's not going to be a cross of the x-axis, but it's going to be a turn. If it appears twice, it's this kind of turn. If it appears 4 times, it's a slow turn. If it appears 6 times, it's a much slower turn. Still one intercept there, but much slower. It takes its time. So then I established what this represents, and I established what this represents, multiplicity 1. I will put them in the chart. I will have 0 and 3. I will make myself a note At 0, is it a cross or a turn? Multiplicity 2 for x equals 0. Is it a cross or a turn? Very good. I make myself a note because I may forget. X equals 3 is multiplicity 1. Of course, this is 0 and this is 0 because the y is 0 for both. What do I write on top of 3 comma 0? Do I write a cross or do I write a turn? Cross. Is it a slow cross or a regular cross? Since it's multiplicity 1, it's a regular cross. It does not take its time. It's fast. Okay, so I'm going to put in parentheses fast. Very good. So now back to our list. Yes?
Why is 0 a candidate?
Multiplicity 2, which is an even multiplicity. Multiplicity 2 is always a term. An odd multiplicity, multiplicity 1, is always a cross, but it depends on what type. Better? Good. So back to our list. This is accomplished as well. Now the y-intercept. Can anyone tell us how to determine the y-intercept for any function? Good. I already have it. It's already there. This is the x and the y-intercept. So this is done. Maximum possible number of turns. So let's look at x cubed for one more time. This is x cubed, correct? How many turns does x cubed have?
3.
That's degree. Okay, follow my hand. Here's x cubed. How many turns?
2. Right? 1.
Turn means this.
I see. So maximum or minimum.
Exactly. So x cubed doesn't have any. The maximum possible number of turns that a function can have is the degree minus 1. So we have to write that down. Maximum possible
Degree minus 1.
number of turns equals degree minus 1. What is the degree of x cubed?
1. No, 2. No, fuck, 3. That's how you know I'm tired.
So the degree is 3. What is the maximum possible number of turns that this function can have?
2.
2. How many does it have?
None.
None. So it doesn't have to turn twice, but it cannot turn. If it does turn, it cannot turn more than twice. Okay? Now, in our case, this function has degree 3, as you already told me. What is the maximum number of maximum possible number of turns for this one? It's degree 3 minus 1. So how much would that be?
2.
2. Very good. So it cannot have more than 2. It cannot turn more than 2. It doesn't have to turn. Okay. So we are back to our list. Maximum possible number of turns, always the degree minus 1. Now we're talking about end behavior.
That says it approaches either infinity, right?
I agree. Two types of end behavior. For odd degree and for even degree. Can anyone give us a function that has odd degree and we know everything about?
X cubed.
True, we know about x cubed as well. Now, I'm referring to even simpler than that.
X.
Exactly, linear function. What are the possibilities for a linear function?
Straight line. That's it.
which means the leading coefficient or the slope is what type? Positive. And the second option is all odd degrees will follow one or the other. All of them. So odd degree can do this from negative infinity to infinity if the leading coefficient is positive, or can do this from positive infinity to negative infinity if the leading coefficient is negative. Any odd degree polynomial function will follow one of the two patterns. If the leading coefficient is positive, it will come from negative infinity, go to positive infinity, and this is the end behavior. If the leading coefficient is negative, it will come from positive infinity, go to negative infinity, and this will be the end behavior. Can anyone give us an example of an even degree polynomial function, the simplest possible on the planet, that we know everything about?
X squared.
X squared. What are the two options for x squared? If the leading coefficient is positive, how does it look?
As a minimum.
Right. If the leading coefficient is positive, it has a minimum. What is the end behavior? Coming from
It goes from negative infinity to infinity either way, actually.
from what's up here?
Infinity.
Yes. Going back to,
Positive infinity.
so that's the end behavior when the leading coefficient is positive.
I see.
The other option is when the leading coefficient is negative, what is the end behavior? From
Negative infinity.
to,
Back to negative infinity.
that's it. Every even degree function will follow the same pattern. So it will be from infinity to infinity if the leading coefficient is positive. And it will be from negative infinity to negative infinity if the leading coefficient is negative. All even degree functions, degree 4, degree 6, degree 8 will follow this. All odd degrees, degree 3, degree 5, degree 7, and so on and so forth, will follow this.
We're talking about range, right?
Not really. Not really. We're talking about,
What happens once you reach the end of the graph? Sorry.
thank you. When x approaches negative infinity, where the function goes. When x approaches positive infinity, where the function goes.
Oh, okay.
So it's not about the range. It could be connected, but it's not per se the range. Good. So let's come back. Okay. What is the leading coefficient of this?
Three.
What is the leading coefficient?
1. Negative 1.
Negative 1. Agreed?
Yep.
Because this is specifically, they did that to us so that we are not ready to read the leading coefficient. We have to rearrange it in descending order. So it is a negative 1. I go back to my explanation here. Is the degree odd or degree even? The polynomial
Odd.
we're looking at. Is it degree 3, right? So it's odd. Okay. Since the leading coefficient is negative, what will be the pattern? Will it be this or will it be this? Number 1 or number 2? Number 2, which means the end behavior is from,
From infinity to negative infinity.
that's it. Go back to my chart. From infinity to negative infinity. That is the end behavior. Okay, that was the end behavior. We talked about symmetry a long time ago, it seems like it. And the symmetry, if you remember, f of negative x equals f of x. What type of function will that be? when f of negative x equals f of x? What type of function would that be? Has nothing to do with the degree. It is an even function, symmetric with respect to the y-axis. Negative x and x are the same. I mean, f of negative x and f of x are the same. What if this equals negative f of x? What type of function will that be?
Odd.
Yes, this will be an odd function, symmetric with respect to the origin. Okay, very good. So if I replace x by negative x here, this will not change, but this will. So the function will not be symmetric. Not symmetric. That's why we studied symmetry in chapter 2. So this is done. This has to wait because I need to use the graphing calculator. Okay. We are now in the position, after all this talk, we're now in the position to graph this function. So please follow my hand. From positive infinity, the function comes to the x-axis and turns at the origin. One more time. From positive infinity, comes to the origin and turns. It has to come to a maximum point because it comes back to the x-axis, crosses straight at 3, 0, and goes to a negative infinity. From the beginning, one more time. From positive infinity, comes down to the origin where it turns. It has to come to a maximum. Why? Because it comes back and crosses at 3, 0 and going to negative infinity. So this is our take on the graph. All I need is not those 15 pages in the book, but all I need is this chart. So it's coming from positive infinity, and it must turn at the origin. That's my first point. 1, 2, 3. This is my next point. It has to have another turn here, and it cannot have more than 2. It already has 1. So it has to turn somewhere. I don't know where, and I don't know how high. You can say, what if you go up here? It's possible. I can't determine that. That's why I have this final item, number 8. So it must come to a maximum because it has to cross again at 3, 0, and it's going towards negative infinity. So this is the graph of f of x equals 3x squared minus x cubed. We will put it in the graphing calculator. You want to go back to y equals. So this is 3x squared minus x cubed, correct? Yes. Minus x to the 3rd power. And since I have the graph, I know what to expect. I'm going to say, okay, the standard viewing window, zoom 6 is fine. Let's see what it gives us. I don't know why it doesn't show here. It should show here. Okay, so it's coming from positive infinity. It turns at the origin, has to come to a maximum, and come back and cross at 3, 0. All these functions, we call them continuous. So when you graph a polynomial function, if you have to lift the pencil off the paper, something is wrong. It's not a polynomial. So as you see, we graphed it without lifting, without lifting the pencil off the paper. They are continuous functions, no gaps in the function, no jumps, nothing. Now, in order to determine this point, the maximum, I will use, so I see the maximum that I'm interested in. I see that this is a local minimum. I don't need anyone to tell me that. It's 0, 0. But between 0 and 3, there is a maximum. So I go to second and calc, and I look at 4. I will give the values where the calculator should look for a maximum between 0 and 3. So my left bound is 0. My right bound is 3. I don't want to guess. I click again, enter, and it will give us the maximum. So I will put it in the chart is 1.99. I'm going to say roughly 2. and the maximum is 4. I go back to my graph. Here's my chart. So this is a turn, so this is a local min, and this is a local max, and this is the local max, 2, 4. Now we know absolutely everything about this function. No one can tell us anything else. Yes, it took us a while because I had to explain each and every